Okay, so today we talk about section 6.3. This is where we talk about the inverses of trig functions. So this is going to take a little while for us to build up, just try and pay close attention to what's happening and understand the argument. So let me give you an example of something that we might have. Okay. So let's say there's a house down on the ground, okay, and up in the air there's an airplane. Okay. Don't get jealous of my drawings. Okay. So here's the ground. It's a parallel line. Okay. We could extend a parallel line from the nose of the plane. It would be parallel to here. Okay. The airplane is a given distance from the ground. Okay. We'll say that's 475 feet. Okay. Now we're going to make the assumption that the ground is flat, and so we can put in a right angle here. Now, someone at the house could be looking up at the airplane. Okay. And this would be an angle inside of here, and this would be an angle of elevation. Now, similarly, the person in the plane could be looking down at the house, and that's another angle that's right here. And this is known as the angle of depression. Okay. And let's say that we actually know that this is 850 feet between them, from here to here. Now, we have to think about some things. What is it about this angle of elevation, depression, and this angle of elevation? We can ask ourselves about what these angles are. So we have to remember something from geometry, that when you have two parallel lines, okay, so here are two parallel lines. This one's parallel to this one. Okay. And it's being cut by a transversal, okay, meaning a line that cuts across it. Now these two angles are known as alternating interior angles. Okay. Here and here. Okay. And from geometry, we know that alternating interior angles are equal. So what that means then here is our angle of depression has to be equal to the angle of elevation, because they are alternating interior angles. Okay, so that's fine. Now let's just call these, since they're equal, we'll just call it theta. Okay. So let's see if we can actually find out what these angles are. Okay. Well, what do we know? We know the opposite. Here's a right triangle. Okay. And we know that the opposite of this angle over the hypotenuse would be the sine of the angle. So we know that the sine of theta is equal to 475 over 850. Okay. We could reduce this. But that doesn't tell us anything about the angle itself. What it's telling us about is this ratio of the sine, okay, of the angle, the opposite over the hypotenuse. So we need a way to undo this, and I alluded to this last time, that the trig functions, under certain restrictions, which those restrictions we're going to learn about today, has an inverse. Okay. So the inverse is noted by a -1, just like f inverse is. I could take the inverse sine of both, and then the inverse and its function will undo each other, excuse me, leaving just the angle. And then the angle is, in exact values, the inverse sine of this ratio. Okay. This is the exact value. Okay. We could put it in our calculator and get an approximation, but we won't be using our calculators. So this is how you'll be leaving things on your exams, okay, and on your homework. So this is the exact value of an angle. Another way, okay, so notation. This is the inverse sine of an angle. It's also equal, sometimes you'll see it written as arc sine. Okay? They mean the same thing. We can do it with all of them. This is the inverse cosine, also known as the arc cosine of theta. And tangent, we could do it with the other three as well, but you get the point here. This is the arctan of theta. Okay. Alright, so that's a quick introduction to how we use the inverse sine, and a specific example working with it and some notation. But now, let us review what inverses are so I can actually start telling you about how the inverse trig functions come into being. Okay. So recall that there is symmetry in inverses. That is, inverses are created by switching the x and y coordinates. Okay. Of an ordered pair. All right. So let's say, for example, we have this graph. Okay. So inverses are created by x and y by switching x and y coordinates, which leads to symmetry with respect to the line y is equal to x. Right. So let me put that line in, our 45-degree line. And this is the line y is equal to x. And now let's look at just one half of the parabola. That is, so if we just look at the point 0, 0, okay, then there's also the point 1, 1, okay, and then we would also get the point 2, 4. Let me draw this in so it looks nicer. Okay. And then we'll put this in and say this is 2, 4. Okay. So this is our function f of x. Now, if I want to switch the x and y coordinates, the 0, 0 will stay the same, the 1, 1 will stay the same. Okay? But all of these points in between here will come up like this, and it will come out like this. So this would be the point 4, 2, okay? And this would be f inverse of x. Okay? So not a trig inverse, but certainly an inverse. So you could say this is the inverse to that, or you could say this is the inverse to this. Okay, it's a relationship that they have. And notice that each graph on their own is in itself a function. Okay, this one is also a function. Okay? Not together, but on their own. Now, let's remember some rules. Okay? We know by function composition, that is, if you take f inverse and you compose it with f of x, what that means is that I'm taking f inverse and into it I'm putting f. Now once I do that, by function composition I should just get x. That is, it should undo each other and I'll get with what I started. And now this will be true for all x in the domain of our inside function here, which is f. And by function composition, if they are inverses, it has to work the other way as well. If we take f and compose it with f inverse, we get f composed with f inverse. Well, if they are inverses, again, this has to equal x. And this will be true for all x in the domain of f inverse. That is what we're saying, is that functions and their inverses undo one another. This is going to be true, excuse me, this is going to be true for trig functions as well, but we do have some restrictions. I'm just going to keep mentioning that there's restrictions, and once I build this up, I think that you will see why. Okay. So now, we remember by definition, a function passes the vertical line test. You saw me do that just on that last example. I was drawing vertical lines through. Okay, so we know that. Why is that? It's because of this definition of a function. A function is a mapping such that each member in the domain corresponds to exactly one member in the range. So this we know. So now let's look at this mapping a little bit more closely. Given our sine function, I would like to point this out. Now when we start mapping the sine function, let's look at, okay, so here's 2 pi. Here's pi over 2, here's 3 pi over 2, okay. Down here's negative pi over 2, half that's negative pi, half that's negative pi over 2, half that's negative 3 pi over 2. Okay. Notice then our x-axes are angles. Okay. So what that means then is that the domain is made up of angles. Okay. And then in our y-axis, the sign can go from -1 to +1. These are ratios. Okay. So our domain is angles, and our range is ratios, okay? Not angles. Now with the sine, we know that if the angle is 0, the ratio is 0. Okay? So 0 maps to 0. Okay? But we also know that sine middle and ends at 0. So also pi and 2 pi map here. Okay? Also these negative values as well. Now at pi over 2, the angle is 1. Okay, so at pi over 2, it maps to 1. And at 3 pi over 2, it maps to negative 1. So, if I just draw in one cycle, it looks like this. Okay. But I may as well draw in the others. This will be negative 1 and positive 1. Okay. So I've completed 2 cycles here of the sine function. And this continues on infinitely in both directions with the oscillations. Okay. So here's our map. And we can see that it passes the vertical line test. Okay. Also, if we do the mapping, we can see that it fits as well, because this member only goes to one member, 0 goes to 1. Pi also goes to 0, but only to 0. It's not like pi is going to 0 and to negative 1. Okay, so it fits the definition of the mapping. This is the map for our function f of x is equal to the sine of x. Now what can we say about this domain? Because it goes on infinitely. The domain here goes from negative infinity to infinity, okay, because I can do it in both directions. The range, on the other hand, is restricted from negative 1 to positive 1. That is what we know about the sine of x. Okay, let's remind ourselves about one-to-one functions. Okay, so now one-to-one functions the key thing that we like about them is that one-to-one functions have inverses that are also functions. One-to-one functions, we can tell them very easily because they pass the horizontal line test. Okay, so one-to-one functions have inverses that are functions, and one-to-one functions pass the horizontal line test. Okay. Now, I've told you that the trig functions have inverses, okay, inverses that will be functions. However, you can clearly see from here, if I use this horizontal line, it cuts just on these 2 cycles 4 times, but it'll cut an infinite amount of time. So this is not a one-to-one function. And so that's going to lead us to problems. Okay. All right. We're going to come back to this. Okay. I'm going to tell you a little bit more about the inverse trig functions before we actually start building them up. Okay. Now, this is the map that you need to keep in your head, okay? So we said earlier that here we have a group of numbers, and let this be the domain, and let this be the range. Okay. Now, the domain for the trig functions, okay, I'm going to have some trig function here, it doesn't matter which one I pick, but the domain here are angles. That is, I find the sine of 45 degrees. And what comes out is the range, square roots of 3 over 2, and this is a ratio. Okay. So that is, these numbers are the domain for the trig function, and these numbers are the range. Okay. So domain is angles for the trig function, and the range of ratios. Okay, well, if I want to undo that, then I need to have the inverse trig function, which will start from here and take us back. Now this is the part where we're going to get confused, okay, especially when our notation comes in. So what I put into the trig functions are ratios. That is, this is the domain for the inverse. Okay, so into the inverse go ratios, and what comes out are the angles. Okay. So let's look at an example of what this might mean. Okay. So for example, if we were to evaluate the inverse sine of root 2 over 2, okay, what does that mean? Okay, so here's a ratio. I put it into the inverse trig function. Well, what that means is to find an angle whose sine is root 2 over 2. Okay, so that's fine. So we can think about it in multiple ways, right? Well, the inverse sine of root 2 over 2, well, I can tell you an angle, pi over 4. Okay, no problem. Here's a quick sketch of my unit circle. Now the sine is the y values. Okay, so it happens in two different places, here at pi over 4 and here at 3 pi over 4. Okay, so I've got two of them. There's 3 pi over 4. Well, that's not the only ones, though. I mean, I could keep going. There's an infinite amount of angles, right? Here's my first one. I could also loop around and add 2 pi to that. Okay, so, well, 2 pi is 8 pi's over 4. So 8 pi's over 4 plus pi over 4 is 9 pi over 4. I could take this one, and any angle that's coterminal with it, say, again, just one looping of pi over 4, of 2 pi, is 8 pi over 4. So 8 pi over 4 plus 3 pi over 4 is 11 pi over 4. Okay. And I could keep going. I could also look at the negative angles. Okay, so if I went in negative rotation, this is negative 1, 2, 3, 4, 5 pi's over 4. Okay. If this is negative 5 pi's over 4, 6, 7 pi's over 4. Okay. And that's just a few. There's an infinite amount. And this is a problem, okay, because if we want the inverse sine to be a function, I cannot have it map to multiple values in the range. Okay? It can only map to one value in the range, right? So I can only have it be one angle. So this is a problem. And we can see that problem happening because, now, just to show you this again, if this is sine, it's oscillating around the y-axis, the x-axis. Okay. Now, if I take the y equals x and I flip every point, what's going to happen is it's going to oscillate around the y. Okay. So the way that looks is now, instead of the range going from negative 1 to 1, the domain goes from negative 1 to 1. Okay. And I can put in 2 cycles. Here's 2 pi. Here's pi. It's pi over 2. 3 pi over 2. Because now this is the ratio, and this is the angle. Okay. And down here, negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. Okay, and so these things need to flip. So instead of pi over 2 comma 1, I have 1 comma pi over 2. Okay. 0, 0 will stay the same. Okay. Now instead of the point pi 0, I have 0 pi. And also instead of the point 2 pi 0, I have 0 comma 2 pi. And then also out here, we'll get the point negative 1 comma 3 pi over 2. Okay, so if we think about it that way. Then down here, we would have negative 1, let's come out a little bit further. Negative 1 comma negative pi over 2. And then the zeros. And then over here. Okay. So now if I was to connect these, okay, and then of course it would just keep oscillating up and down. Okay, so this is y is equal to the flip-flop of the coordinates, the inverse. Okay. This is actually the graph of x is equal to the sine of y. Okay. The important thing to realize here is this a function? And clearly it's not a function. Okay. No matter where you draw these vertical lines, we do not have a function. Okay, so this is not a function. And that's a problem for us, right? But just like as an aside, remember, if this is y is equal to x squared, it does have a function, inverse, y is equal to the square root of x. Okay? And the way we found that was simply by ignoring this part of the domain of y equals x and just inverting this portion of it. So we restrict the domain to get the inverse here. Okay. So we're going to do the same thing. We need to restrict. Alright. Now the way they've done that is actually, now people just got together and decided this, okay? So it's just something we all have to agree upon. And they said, let's just look at this portion from here to here. Okay. So let me pull that out so we can see it a little bit better. Okay. So from negative 1 to 1, it is just this portion that looks like so. Okay. Where this is the point, it comes up here to pi over 2, and this is the point down here at negative pi over 2, so this is negative 1, negative pi over 2, and this is 1 comma pi over 2. So this is y is equal to the inverse sine of x. So this is what we need to know. Now its domain now goes from negative 1 to 1 inclusive. And what comes out then is the range, and this is where it's going to start giving us problems. We'll have the negative angles from negative pi over 2 through 0, and then 0 through the positive values of pi over 2. Okay. And because this is going to be a problem for us, I have a little picture that I like to draw. I reference everything back to the unit circle. So when I'm drawing that, the values that will come out on the unit circle will start here at positive pi over 2. Okay. But now this is not 3 pi over 2, it's negative pi over 2. Okay, because of the restricted values that were chosen for us. And I can take any value in between here is what will come out in the range. So this y is equal to the inverse sine of x is equivalent to x is equal to the sine of y. But the important thing here is to remember these restrictions and also what you can put into it. You know, we can't put a ratio that's larger than 1 or more negative than negative 1. All right, let's try and put some of this into action. So let's do some evaluating. Let's say I need to find the value of the inverse sine of 3 pi, not 3 pi, root 3 over 2. Okay. Now remember, what goes in, this is a ratio, and what comes out needs to be an angle. Alright, so I always draw a sketch. Here's our unit circle. Okay. Now the sine is the y values, and so when it's the root 3 over 2, it happens in two different places. Here at pi over 3, and let's see, 2 pi's over 6, 3 pi, 4 pi's over 6. So this is 2 pi's over 6, 2 pi's over 3. Sorry. Okay, so those are two angles. Okay. Just in one looping from here to here. Okay, so just in one rotation, I have two different choices. But remember, I could do all the loops. But that won't be a function. So now that we've restricted the inverse sine, we have to ask ourselves, well, which one is it? And this is where that shading becomes very helpful to me. Okay. The inverse sine returns in this range. Okay. So I know the angle I have to pick is pi over 3. Okay. It is not 2 pi over 3. Here's another one. Let's look at the inverse sine of negative square roots of 2 over 2. Okay, so here again is a ratio that I'm putting in. And a good way to think about this is really saying, tell me the angle whose sine is negative root 2 over 2. Okay, well, I like to draw the picture. So where the sine is negative root 2 over 2 happens in two places on one looping in the unit circle. Okay, now, so this is, let's see, 1, 2, 3, 4, 5 pi's over 4, 6, 7 pi's over 4. So which is it? So again, I'll draw in where the inverse sine comes. I'm closing these circles in because they can have values there, and it goes this direction. Okay. Now the thing I have to remember is this is the positive loops to pi over 2, and this is the negative loop. Okay. So we know this is the location of the angle that the inverse sine will return. However, the inverse sine only goes from negative pi over 2 to pi over 2. So we've written this as a positive rotation of the angle, and that's not the one the inverse sine will return. The inverse sine will return the negative rotation of the angle. So the angle that is coterminal with 7 pi over 4 is negative pi over 4. Okay? 7 pi over 4 is not in the range of negative pi over 2 to pi over 2. Okay? So what this returns is negative pi over 4. So this is going to take a little bit of practice, okay? Alright, let's try another one. For example, let's try the inverse sine of negative 1. That is, tell me the angle whose sine is negative 1. Okay, I'll give you just a minute. So with the inverse sine, tell me the angle whose sine is negative 1. We know 3 pi over 2 is where this occurs. But again, let's think about the restrictions here. Okay. And in the restrictions, this is pi over 2, and this is negative pi over 2. So what our inverse sine returns is negative pi over 2, not 3 pi over 2. Okay. Because it is outside the range of negative pi over 2 to pi over 2. Okay, let's keep going with the inverse cosine. There's plenty of time to practice this with your homework, and it will take some practice. Okay? This is where coterminal angles are going to be very important. All right, so without building up all of the inverse cosine again, let me just say that if we have y is equal to the inverse cosine of x, well, that means the same thing as the cosine of y is equal to x. And without drawing the whole thing, when you flip-flop the cosine values, the x and y values, okay, here's 1 to negative 1, okay, here's 2 pi, here's pi, it's pi over 2, there's 3 pi over 2, okay. Now this point is now 1 comma 0, and up here we now have 1 comma 2 pi. Halfway in between that is negative 1 comma pi, and then the zeros are in between. Okay. So this is just one cycle where the ordered pairs have been flip-flopped. Okay. So this is y is equal to the cosine of x in one cycle. And we can clearly see that this is not a one-to-one, it's not a function because our original was not one-to-one. So the restrictions here decided to take from here to here to be the inverse cosine graph. Right, so if we pull that out, so you can see it just a little bit better, if you had to graph the inverse cosine, okay, it would start up here, middle there, end there. So it would be like this and like this. Okay, so this is now up here to pi. Okay, this is pi over 2. Okay, this is the point negative 1 comma pi, and this is the point 1 comma 0. Okay. So from here, we can see that the domain, this is y is equal to the inverse cosine of x. That's all it is. Notice it's not an even function. You can't go flipping it around. It doesn't work like that. Even though cosine's even. Its inverse is not. Okay, so the domain goes from negative 1 to 1 inclusive. And the range now starts at 0 and goes all the way up to pi. So the little sketch that I draw then, here's our unit circle when I'm dealing with the inverse cosine. This one's pretty fun. Reminds me of a person wearing headphones. Okay. It can go from 0 to pi and anything in between. So what's nice about this is that all values in the range are staying positive. Unlike with the inverse sine, we had to worry about negative, converting to the negative angles. Okay. So now, let's do some evaluating with this. Example. Let's find the inverse cosine of square roots of 3 over 2. Okay. This is an angle. I'm sorry, this is not an angle. This is a ratio, and what will come out is an angle. Okay. So when you read the inverse cosine of anything, you're really talking about an angle. So tell me the angle whose cosine is square roots of 3 over 2. Tell me the angle whose inverse cosine is square roots of 3 over 2. Okay, well, where the cosine is equal to square roots of 3 over 2 happens twice on one looping. Okay? Happens here at pi over 6 and here at 11 pi's over 6. Okay? Now, I remember to pick which one I'm going to use. Here is the restrictions of inverse cosine. Okay? And then from there, it's very clear that the angle I'm talking about that is in this range is pi over 6. Here's another. Let's look at the inverse cosine of negative root 2 over 2. This is an angle. This is really saying, tell me the angle whose cosine is negative root 2 over 2. Tell me the cosine whose angle is negative root 2 over 2. Okay, well, where the cosine is negative root 2 over 2 happens two places in one looping, here and here. This is 1, 2, 3 pi's over 4, 4 pi's over 4, and 5 pi's over 4. And then to decide which I use, I draw in the restrictions. And once I do that, it's clear that the angle that meets the domain restrictions, or the range restrictions here, is positive 3 pi over 4. Let's do one more. What about the inverse cosine of negative 1? Okay. So this is saying, tell me the angle whose cosine is negative 1. Tell me the angle whose cosine is negative 1. Okay. Well, that happens right here. Okay. Negative 1. Right. And luckily that is within the restrictions. That would go from here to here. So the inverse cosine of negative 1 is equal to pi. Okay, so the inverse cosine is easier to deal with than the inverse sine, but we need to be comfortable with both of them. Now, the inverse tangent might be the most versatile of all of the inverses. Let me show you why. So if we're graphing y is equal to the inverse tangent of x, well, that means that I'm flip-flopping things, so I'm taking the inverse, or the tangent of y is equal to x. Okay. So this one, let's look at one cycle of tangent. Now, one cycle of tangent goes from negative pi over 2 to pi over 2. Okay? And it looks like so. So if I'm going to flip-flop these values of x and y, what will happen then is that these vertical asymptotes are going to become horizontal asymptotes. Okay. So this is negative pi over 2, and this is pi over 2. When I flip-flop everything. Okay? And then the inverse tangent is going to come up like this and get asymptotically closer to each of these asymptotes. Okay? So this is y is equal to the inverse tangent of x. So this is why, if we look at the domain, now with the inverse tangent, the domain it goes from negative infinity to infinity, and this is why it's the most versatile, because we can put in any input. any angle. So that makes it very, very versatile. And then what's going to come out, well, it'll start at negative pi over 2, but there's an asymptote there, so it can't include it, and go all the way up to positive pi over 2, but again there's an asymptote there, so it can't include it. So in this way, the inverse tangent is nearly identical to the inverse sine, except now I'm going to draw open circles here at positive pi over 2 and an open circle at negative pi over 2 because I have to leave out the asymptotes. And again, we'll have that problem of we have to get the coterminal angle in the negative space. Okay. So now let's work with some examples. So, for example, let's find the inverse tangent of negative 1. Alright, tell me the angle whose tangent is negative 1. Tell me the angle whose tangent is negative 1. Well, it might be easier to think about that in terms of negative 1 as either being negative root 2 over 2 divided by positive root 2 over 2, or the other option to get a negative 1 inside of there would be the positive on top divided by the negative on the bottom. Okay, so if this is the sine, negative root 2 over 2, I'm down here, positive, okay, that would happen here at 7 pi is over 4. Okay. Now in this case, the sine is positive, but I need to be negative in the cosine, so it would also happen here at 3 pi over 4. Okay. So now we have to think about these restrictions, and which of these angles will it be? Okay, so the restrictions of the inverse tangent mean I can't have, because of the asymptote at pi over 2, and I can't have an angle here because of the asymptote at negative pi over 2. Now the angles that are in here will be acceptable. Okay. So 7 pi over 4 falls where we've drawn it, however it doesn't fall in this negative restriction. Okay. To be in between 0 and negative pi over 2, we have to look at the negative rotation of this. And remember, 7 pi over 4 is coterminal with negative pi over 4. So the inverse tangent of negative 1 is negative pi over 4. Okay, let's do another one. For example, what if we had to find the inverse tangent of root 3? That is, tell me the angle whose tangent is root 3. Alright. Well, again, let's do this little trick that we did up here. This is equal to, well, the inverse tangent of, we could just rewrite root 3 as root 3 over 1, which doesn't still quite help us that much. But I could write this as the inverse tangent of, and now I can divide both top and bottom by 2. Now with that, that'll be very helpful for us, because remember, this is going to be the sine, and this is the cosine. But also remember, we'll have one more option. We could have it be that it's the negative divided by the negative. Okay, so we do have two options on one looping to consider. So here's our unit circle. Okay. I need the sine to be square roots of 3 over 2 and the cosine only to be 1/2. So that works here at pi over 3. Okay. Now if we need the sine, okay, the negative cosine and then the negative sine, so this is 6 pi over 6, 7 pi's over 6, 8 pi's over 6, so this is 4 pi's over 3. Now let's put in our restrictions so we can determine which it is. This is positive pi over 2, this is negative pi over 2, and we can return anything inside of here. And since this is positive, we can clearly take this to be the angle. So the angle whose tangent is root 3 is pi over 3. Okay. All right. Now there are inverses for the other functions as well. Okay. So, for example, the way you would find that is, let's find an equivalent expression for the inverse cosecant, so the arc cosecant of x. We still get the same definitions, that if you have y is equal to the inverse, okay, these are the same, remember. It just means you're flip and flopping the x and y. So we have the cosecant of y is equal to x. Okay, so if this is what it means, and we want to find an equivalent expression, let's work with this. Okay? So, just recopying it, the cosecant of y is equal to x. Well, the cosecant of y, I could rewrite using the reciprocal as 1 over the sine of y is equal to x. Now, what we're trying to do here is we're going to try and solve for y. Because this is solved for y. Right? So, alright, I want to get that y out of the denominator, so I'll multiply both sides by the sine of y. Okay. And these will cancel. So we have 1 is equal to x times the sine of y. And we can divide through by x because we're trying to get to y. Okay. These x's will cancel. So 1 over x is equal to the sine of y. Okay, now y is in the argument, it's wrapped up in the sign, so I want to undo the sign, and I can do that by taking the inverse sign, and let's just make a note that it's like, we have to make sure this is under certain restrictions, okay? And I'll tell you what those are in a moment. Right. But what I do to one side, I have to do to the other. Okay. So under these restrictions, on the left-hand side, we have the inverse sine of 1 over x is equal to, well, the sine inverse and sine will undo each other, provided we're under the right restrictions, we'll get y. But we also saw from up top that y was equal to the inverse cosecant of x. Okay? So what that means then is if this equals y and this equals y, well then the inverse sine of 1 over x must be equal to the inverse cosecant of simply x. Under restrictions. So what that means then is if you're faced with any of these inverse of the other functions, so like the reciprocal of cosecant is sine, you could take the reciprocal of the argument and they would be equal. And similarly, you could, under restrictions again, the inverse secant of just x is equal to the inverse cosine of 1 over x. And the inverse cotangent of x is equal to the inverse tangent of 1 over x, okay, under restrictions. So these are 3 others for you to know. Okay. And so let's say, for example, if we had to evaluate the inverse secant of 2, okay. Well, I'm going to use this rule then. That's the same thing as the inverse cosine now of 1/2, its reciprocal. And now this means tell me the angle whose cosine is 1/2, okay, and that is pi over 3. All right, let me show you the restrictions. I won't require you to know these. Just know that as it comes up. Okay, so the inverse cosecant, these have domains where you can't go in between -1 and 1, and you'll have to exclude the 0 values. Okay. This is the, let's see, this is the secant's restrictions, and then here are the cotangent's restrictions. You'll run into a problem, I know, when you're in those violations. Okay. Okay, so that's quite a lot for today. Let's stop there for right now, and we will continue next time with the composition.